All right, let's get going. So here's what we've got today, Wednesday the 26th. Looks like a lot of stuff. I put a whole bunch of sort stuff kind of broken out. We're going to do a Unix tip of the day in which we actually show you how to send an email from the command line in a terminal. Kind of interesting. Sometimes you might need to use that. And it's an easy way to get your files from one location to email. And then we will talk about sorting. So this is actually a little bit off from the schedule. I decided to move sorting up just because we actually just did a heap sort. And the next assignment is going to be on sorting, which is coming up tomorrow, which we'll talk about at the end of class. And so we're going to talk about a whole bunch of these sorts. And then at the end, we'll do some of the midterm answers. There's still a couple people who haven't taken the midterm. And I don't want to give up the whole answer key before they do. They're going to do it tomorrow. So we may go over most of the other midterm answers on Monday. Again, if you have specific questions about the the midterm exam, just email me and we can go over it. What I'll generally do is have you come in and we'll go through your whole exam and see how you did. And, for what it's worth, I think, I probably shouldn't admit this, but I think everybody who's come by to see me has gotten at least 1 point back for something or other. So anyway, not to say you should all I'll get points back and whatever. If you thought it was fairly graded, fine. There is one question. It's the one where you have to circle what the operator equals overload is. Some people got points off for something that it was my fault on the grading rubric that you should not have gotten points off. So I will fix that by next week. I'll regrade that page and fix it by next week. So you don't have to email me about that. And I'll let you know about that. OK, questions before we begin? Nope. All right. So the Unix tip of the day. A lot of times I'll do a tip and then just show you on the terminal. But this one's got a couple different things you need to know about it. So it turns out that you can send emails from a terminal command on the server that we have for Linux. You can't do it from just any old Linux server. It has to be set up properly. But what you can do is you can send an email by just typing mail-s and then the subject in quotes. Those should be regular single quotes. And then the email address you want to send it to. And then it will pull up a little place where you can do the body of the email. And you type in the body of the email and then hit Control-D, which means like end of input, on a separate line. And then it will, well, it'll ask you if you want to have a CC address. And then it'll blast it off. OK? Let me show you how that works. I see some people writing this down. But it's pretty straightforward. I mean, it just basically is a command line interface for sending a mail. Let me show you that. I know people are writing it down. Well, I'll show you it here. So let's see. Oops. It logged me off. Hang on. OK, so let's see. This. All right. Just 1 sec. OK, so let's see. Here we go. So if I type mail-s and then howdy Chris and then my email address, which is the one I'm sending to, not your own email address. It will send from the username that you are. OK, so I'm going to send this to me, right? And it's going to have the subject line of howdy Chris, right? And then it will go into it'll do a blank line and it'll be kind of waiting for your input. And you can say, hey Chris, sorting is cool, something like that, right? And then if you go to the next line and hit Control-D, right, it will say, hey, do you want to CC it to anybody? And if you don't want to, you just hit return. If you do, you put an email address. And that's it, right? And then in like 2 seconds, I'll get an email. OK? And so I just sent an email to me. All right. That's if you just want to send a quick text email. I've done that in lab a couple times with some people to say, hey, remind me about something. And we just type a real quick email and blast it off. So it makes it pretty easy to write an email. And then you can also, if you want to do attachments, unfortunately, the mail program itself doesn't support attachments. But there's another program called MUT, M-U-T-T, which I forget what it stands for, the MUT Mail User Agent, which I guess is recursive in some sense. But anyway, it is another program you can type if you type the following, MUT-X. And that's just so you don't get if you have an editor set up, if you don't type the X, it will put you into an editor like Emacs or VI or whatever. And you can type the email in there, and it gives you some other options. But if you just want to type it straight on the command line like this, you don't need to type anything. You have to type the -X. Dash A is for the attachment, and I'm going to attach the readme.txt, which I think exists in this folder. And then dash S is the subject, same thing, and then the person's name. So it's very similar. You just have to put a dash X and a dash A and then the attachment, right? I'll put this up on the other screen in a minute. When you do that, unfortunately it's slightly different. When you hit return, it brings up a little weird like black on or white on black menu, and then you can type here's the attachment about how cool sorting is, right, or whatever, right? And then in this one, see how it says end the message with a period on a line by itself? I don't know why it does that. I don't know why it's not standardized. But what it means is when you're done, if you hit return and then you put a period on a line by itself and hit return again, it will send your message. Okay? And so now I'm going to get an email that's from me that says it has the readme.txt as an attachment, the subject line being dash the readme file, and whatever I typed in there about how sorting's cool. Okay? Questions on that? Let me bring it back up here so you can see it again. This was the original one with mail. So dash S for subject, and then the email address, and then type away Control D. And then the MUT one, it's kind of hard to see from back there, MUT dash X dash A, the file, dash S for the subject, and then the email address, and then the period in the end. Yes?
If the file doesn't exist, does it give you an error? Does it just send it without an attachment?
It's a good question. Let's try it. No idea what it does. Let's see. Dash A, not a readme.txt. Nope, it says unable to attach file. So, yeah. It didn't send anything because I didn't actually type a message. I don't think it did. If it does, I'll let you know. But I don't believe it does. I don't think it actually sends anything. Stop. Okay. All right. Questions on that? How to send email via the command line? Okay. Nope. All right. Okay, so let's jump right in to this next topic, which is actually one of my favorite topics because there's a lot to it, and there's a lot of different ways to do sorting. Now, we've talked a little bit about sorting in here before, but it's kind of a fun subject as far as I'm concerned. It's kind of interesting in that there's so many different algorithms to do sorting. Okay, and what we want to find is some good ones that that have fast running times and some other parameters that are some other kind of qualities that we'll get into talking about that are interesting. Sorting is actually, believe it or not, still somewhat of an open problem. Like, in other words, people are still thinking about different ways to sort objects in an array or whatever other kind of sort whatever other kind of structure you want to put it in, which is kind of cool. I mean, the first sorts for computers came out in like 1950, right? It's a long time ago, and that's a lot of years that people are still thinking about it. In fact, if you've ever programmed in Python, the Python language actually changed its sort algorithm about, I want to say about 4 or 5 years ago, maybe 6 or 7 years ago at this point, to a brand new sort that some guy named Tim came up with. He calls it Sort. And it actually is a really fast sort, and he published it, and the people who write the Python language are like, hey, that's a pretty cool sort. It's actually faster than the other ones. Let's use it. Boop, and they plopped it in, and it's used. So, in the recent years, we still have some sorting, algorithms coming up, new sorting algorithms. Kind of fun. Sorting is obviously putting things in order. That's all there is to it in the kind of the big picture, right? Most of the time we do it numerically or alphabetically by lexicographical, right? Hard word to say. But you can sort by any key. I mean, as long as you have a comparison, ability to compare, kind of like what we talked about with priority queues and their keys, as long as you can compare two items and you will get a linear comparison based on those rules we talked about a few lectures ago, you will be able to sort them on that key. Okay, so you can sort in however you want, but you have to have an ability to do it in that order. Okay? Sorting is, there's a couple different things you have to know about sorting, right? You have to have it in some sort of what we call a non-decreasing order, which sounds silly. Why don't you just call it increasing order? Well, non-decreasing order just means that each element must be no smaller than the previous one, or the other way around. I mean, if you said it was non-increasing, it would be each element must be no greater than the next one. It doesn't actually matter. You can sort in one order or the other they will both be sorted based on whatever your desire is for the order of the sort, either ascending or descending, depending on how your order is. And you have to be some sort of permutation of the input. You can't go changing keys on you during the sort, right? The input has to be just whatever the input is, rearrange those elements such that they are now in this order. Okay, that's what sorting is all about. Okay. As I said, sorting is a pretty well-researched topic. All right, it's not trivial to do some of these sorts. Okay, you might think some of the sorts we've done are more or less trivial, right? But it's not trivial. And like the Tim sort was from 2002, and some guy Tim is now like in Python, right? Fundamentally, if we're doing comparison sorts, that means we're comparing two values and then making sure they're in the right order. For n values, if you have n values, you can't do any better, and this is provably so, you can't do any better than order n log n. Just not going to work. Now, there are other kinds of sorts not based on the direct comparison where you can do slightly better, but in the end, it's going to degenerate to this generally, right? Somebody mentioned in here the other day, I forget who it was, somebody from like this side of the room, I forget who it was, said, hey, what if we took the integers and we were sorting integers and we just put the integer in the array location of that integer, like whatever integer it is, that's the array location it should go into, right? Well, that's actually kind of cool. You can sort the elements that way in order n because you can actually, if you have a big enough array, you can actually sort it that way, right? But the thing is, we also have to consider the amount of space that we're going to use when we're doing these sorts. Okay? What do I mean by that? Well, that means that some sorts you can do such that they are in place. In other words, you start with an array this big and all the elements are in there. And then what you're doing during the sorting is moving those elements around inside that array, which doesn't need extra memory, another array. Okay, does that make sense? Where you could do it another way. I mean, you could take one array and then just pick pieces out and move them into another array. And that's one way of doing it. But then you have two things that are this big that you need to allocate space for. And when you're talking about really large data sets, you don't want to have take up more space than the amount that you have for just the data itself. If you can do it, what we call in place, that's awesome. Okay? So that's what we mean when we say in place. And that can be really important if your data sets get huge. Okay? For small data sets, it doesn't really matter. An example is the heap sort we used in lab over the last couple days. That actually, I'll show you the code for that. You might not even seen it. It's in the main function. It actually has the heap. Then it has two more arrays that it's kind of moving elements back and forth in, so that you can do that sort in. But it's not in place because of that. Okay? Questions on that? All right. We can also have this interesting idea of a sort being either stable or unstable. Okay? What that means is that if you have the same key in an array, or in whatever, if two items have the same key, if they start in this position, they will end up in the same position after they're sorted. They should still be next to each other, right? Or yeah, they should still be next to each other, but they won't swap somehow in the middle of the sort. And that is important for some types of sorts. Nothing that we'll probably worry too much about. Like, who cares if it's in the other order if they're the same key? But sometimes you actually care about that. Okay, and that's what sorted, or that's what a stable sort means. An unstable sort means that during the sort you could end up swapping elements that are the same key, and they just end up in a different order than they started in. But not a big deal for most types of data. But if you do need a stable sort, make sure you pick an algorithm that is a stable algorithm. Okay? We're going to have a couple lectures on sorting, right? But for the meantime, there's a couple places you can go if you want a little more information about, like if you want to actually see some of this stuff in action. And I'll show you some as the class goes on today. There is a great sorting algorithm animations website, and I'm going to show you that in a second. There's the other one that I've shown you lots of times, which is pretty good. And then there's also a really cool one, which I'll show you maybe after we get done with one of the sorts. I'll break it up a little and show you this one in a little bit. There's a thing called 15 sorts in 6 minutes on YouTube. And you think, how do you use sorts on YouTube that are like not boring? This is actually cool. You'll see. It's got sound and everything. All right. And then I'll show you one other video, which is amazing. You'll see. OK. So let's see. So let me go to that website right now. And let's see if we can. Here it is. OK. So here's what this is. This is actually kind of cool. So there's a whole bunch of sorts. In fact, we will talk about this sort, the insertion, selection, shell, and heap today, right? We're not actually going to talk about bubble sort. It's a terrible, terrible sort. You should never implement bubble sort. If you have, that's OK. Did you do it in Comp 11? If you did, that's fine. I mean, it's a good one to like learn how to make sorts, but it's a terrible one. Like as far as you'll see in a sec. We're going to talk about a couple of these. Merge sort, Quicksort is a great one, which we'll talk about. And there's this other one here they had thrown, which is Quick 3, which is a kind of a modification of the Quicksort. This is not all of them. If you look at the sorting algorithms, there's like another like 20 different sorting algorithms. These are the ones that some of the ones we're going to talk about. But watch what happens when I click this big button right here. Watch what happens. These are all you can see all these here. This is a random sort, and it's kind of like a bar graph kind of on its end. This would be the minimum element, and this would be this next minimum element, and this would be like the maximum element. And it's the same for all these different sorts. And then they've got one that's nearly sorted, because that actually makes a difference sometimes for some sorts too. If you've got a nearly sorted list, some sorts do better, as it turns out. They've got a reversed sort. In other words, it's completely backwards. What we want is the minimum one on top and the maximum one on the bottom here. Okay, and it's completely reversed. And then this one's where there's some unique ones. Like, in other words, see how this one and this one are the same, and that one's the same as another one down here. If it didn't say click to restart, you'd see that. And so but anyway, it goes all the way across. Now, when I click this little button here, watch what happens. Right? This is kind of neat. What it's doing is it's showing you each one of these sorts in real time as it goes through, and most of them are done. Right? The selection sort actually ended up a little bit worse than the bubble sort in this case. So, well, we'll have to do selection sort as well. But this is an interesting one because it's relatively easy. But you can kind of see this, right? You can also just see one in particular, like what it's doing. What it would be interesting to do is go to this page and then click on one and try to figure out what it's doing just by like the little video, right? Might not be tough. Like things like Quicksort, whoa, right? Weird stuff's going on there. We'll talk about that, okay? But it's fast, as you noticed. It was relatively fast. In fact, you could probably do both. This one with Quicksort will still beat the other one, I'm guessing. Yeah, right? Boop, Quicksort's done, and bubble sort's still cranking away, right? So anyway, so you can do that. You can also click on the one. Oops, you can click on the actual ones in general and see more, like see it in bigger detail. They've got the algorithm here. It's kind of nice. Okay. In fact, this might be a good page if you want to know an algorithm and you can't figure it out to go to for our next homework assignment, which I'm going to have out tomorrow and we'll talk about. But it's about sorting and some of these various sorts. Okay. So it's kind of a cool web page. And then, of course, we have the other one, which, yeah, we've got the other one here, too, that we've talked about before, which, let's see, has a whole section on sorting here as well. All the comparison sorts. And then this one also kind of has different sorts that we will mention and that aren't comparison sorts. Although I guess heap sort is kind of a comparison sort, so I'm not sure why it's in there. But you can click on there and then see all the different types of sorting here, right? So, this is the one we're going to do a little bit later. One of the ones we're going to do, and you'll see, and you can see it in a kind of a different format. Okay. All right. Questions on that? Cool websites that you can go to and get interesting information out of. Okay. And then I'll show you the 15 sorts in 6 minutes in a few minutes. Okay. All right. When we have 6 minutes, I think we do. OK, so we've done a couple of sorts already, right? We have already looked at a variation of the insertion sort. OK, what we've done is we've had an empty array, and we've taken values that were given to us or passed in from some input source, and we want to put them into the array in the correct order, right? And then when you get done with all your insertions, you've got an array that is in the correct order and it's completely sorted. What we didn't do, okay, is an in-place insertion sort. Okay, in other words, start out with an array that's got all the values in it, and then manipulate it in place using this insertion sort method to actually make it sorted. Okay, we could have done that, right? But that's not how we did it for the 2 assignments we've had with these. Okay, but we can do it in place. Let's see how that works. Okay? Here's the algorithm. And it's pretty simple. I don't think it's going to confuse anybody in this one, right? Iterate through the list, starting with the second element. The first one is actually, it may not be in the right place, but it will quickly become in the right place if you do this right. Okay? Start with the second element. At each element, swap with its previous neighbor if necessary, and then repeat all the way down to the right place, okay, to where it stops needing to be sorted, needing to be swapped. So what that means is we would go to 5, for instance. Okay, we'd go to 5, and we would say, does 5 need to be swapped with 9? In this case, we're going to order it from minimum to maximum. Okay, later we'll see the other way around, but from minimum to maximum. Okay, so 5 does need to be replaced with 9, right? And then it's done. And then 5, we actually don't need to, we can go on to the next element, in this case, which would be 10. Okay, so let me show you what it looks like here. So 5 and 9 need to be swapped. Okay, and then we go to 10. Does 10 need to be swapped with 9? It does not, because, of course, we've got, it's already bigger than it. Okay, and so you can go to the next iteration. 8 needs to be swapped with 10. And then 8 also needs to be swapped with 9. So you have to walk your way back down. Okay? Same like that. And then 12. Let's see. 12 and 10 do not need to be swapped. 11 and 12 do need to be swapped, but not 10 and 11. 14 and 12 do not. 2, this one's going to kill us, right? 2 here, you have to swap all the way down. Swap with 14, then 12, then 11, then 10, then 9, then 8, then 5. Okay, I'm not going to show you all the different swaps in this case, but you can do that. Now, can you see how this is in some way similar to what we did for the insertion sort before, right? Really what we're doing is we're propagating all the values that are lower than the one we're at up one, right? You could do this slightly more efficiently if instead of swapping each time, you put 2 aside somewhere, taking up a little more space, put 2 aside somewhere, and then figured out where the point is that you need to put it, move everybody over in one fell swoop, and then put 2 in where it needs to go. So you could speed it up that way, but it's still technically in place because you're not moving lots of different, you just have to have that one extra location. But otherwise, if you want to do it strictly in place, you have to do it this way. Although swap actually needs, to do the swap, you need an extra one too. So in reality, you're not going to gain anything from the space-wise by doing it with this way. But it's a pretty easy algorithm, all things considered. Okay? All right. We have talked about this before, I believe. And then 22 and 43 do not need to be swapped. We've talked about this before. Worst case performance here, n squared. Right? It has to look through all of them, and it has to move up to all of them. Right? Same thing with best performance. Best performance is order n. In other words, it can look through, might already be sorted. Right? If it's already sorted, you look at like this list. If we were to do an insertion sort on this one, we'd look at 2, no need to swap. No need to swap 5, no need to swap 8, no need to swap 9, et cetera, et cetera. And then that only means we go through the list once and we're done. So best case, order n. Worst case, order n squared. Average performance for an insertion sort is actually n squared, but if you've got a small enough number of elements, right, then the performance actually is very fast because n is not very big. We will use that to our advantage. And in fact, insertion sort is such a easy to implement and fast for small enough array or algorithm that it's used in other algorithms that have worse performance when you talk about the whole array. So it actually uses insertion sort kind of at the end, right? When it knows that you've got a small enough array that it's going to be very quick using insertion sort, it'll just revert to insertion sort and then do that last little bit. Okay? It's kind of why one of the reasons we talk about it. Easy, and it's also fast for small n. Okay? Questions on that? We also are doing this in place, so therefore we only need n total, maybe plus 1, n total locations to actually do this. We don't need a whole other array. We don't need extra space. Okay? Yeah, question, Tom. Very good question. How small is a small array? We find that generally empirically. I mean, they do the tests on a lot of like, let's say they have a sort and they go, well, it's not so good when you get to the small, but we can do insertion. they pick it based on lots of tests. I mean, generally, I don't think there's a specific algorithm, but it's generally between 5 and 15 elements is considered small, which is very small. But yeah, once you get more than 15, you're probably going to do better in your other sort that you started with. Yeah, good question. Okay. Anything else in this one? All right. Let's go on to selection sort. Okay, here's another sort that's interesting. Okay, selection sort does the following. Okay, it's another in-place sort, which is good for the space requirements, right? And what it does is it says, here, find the smallest item in the list. Go through the list, find the smallest item, and swap it with the leftmost unsorted item. Okay, and that should make kind of intuitive sense also, right? I mean, if you're going through a list, let me see, do I have this one on the next? Yeah, I do have it on the next page. If you're going through the list, right, finding the lowest one, and then making sure you swap it with the one we already know is lowest up to a certain point, well, then you actually have, or rather, the last unsorted element that you haven't sorted yet, you will definitely put them in order. This is not such a great sort here. Okay, and you repeat the process for the first unsorted element. Okay, let's watch what it does here. Actually, we can see the animation. I've also got it here. It's kind of slow. Like, this is a terrible sort when you're talking about your big O notation. Why? Because it has to go through the entire list every time, find that smallest element, and then replace it. And we did something like this when we were doing the unsorted array priority queue. Remember how we did that? We had to find the element each time and then move it in the right place, right? That was not a little better for the unsorted. But in this case, for it to actually do the sort itself, you need to go through the whole thing and then replace it. So not so great, right? So in this case, we have, let's see, we go through the list, we find that 2 is the minimum, and it swaps with 9. And then we go through and we say 5, oh, 5 is already the minimum, don't have to swap, that's nice, right? Then we go through and we say 8's the next one, swap it with 10, right, et cetera, et cetera. I'm not going to make you walk through this whole thing. Okay? But the performance here is, as it shows here, it's worst performance n squared, best performance n squared. Right? You still have to go through the list n number of times and do that many. You have to go through it that many times and then swap with the first one. So it's not a very good algorithm, best case or worst case, in the terms of time complexity. Space complexity, same thing. We are doing it in place, which is kind of nice. Okay, and it will work out fine that way. This one happens to be a stable sort. If you had elements that were the same order, that were the same key, it would grab the first one first and put it in and keep the order the same. Okay? Selection sort. Questions on that one? You can go look at the animations on that one. In fact, I will show you the animation that I promised you. 15 sorts in 6 minutes. Let's see if I can get it here. Here it is. 15 sorts in 6 minutes. Here we go. All right, now, hopefully the sound's not too bad. OK. This actually has sound. Notice what it's doing here. This happens to be selection sort right here. Right? Kind of fun. I'm not going to show you. I don't think I'll show you all 6 minutes. But this one is insertion sort. OK? All right. This is the insertion one. Not particularly fast. The sound is based on, I believe it's based on which ones swap. If it's higher, it's like a higher pitch, and lower, it's a lower pitch. So notice how long this takes at the end, right? It's got to do all these movements. There you go. Let's see. That was insertion. This one's Quicksort. This is the one we're going to talk about later. This is a cool looking sort, right? You got to love the sound too. Yeah, it does it in halves. Keep in mind, when we're doing sorting, if we can break things into halves, we're going to get log n behavior, right? All right, let's see. That was Quicksort. What else do we have here? Merge sort. We'll get to merge sort probably on Monday. All right. Notice what it's doing, breaking it into pieces again, right? It's already done half, right? This is a pretty quick sort, as it turns out, right? And then, whoop, right? It's kind of fun when it talks about it. OK, let's see. This is a heap sort, which we're going to go to in 1 sec. In fact, I'll stop it after this and go to heap sort. All right. Notice how it's building it, by the way, backwards. Okay. Heap sort is built backwards. We'll see that in a minute. OK. There you go. All right. I'll show you some more of that in a bit. But that's so you can kind of see people have had fun with this. People love doing sorting like visualizations. It's kind of fun. All right. OK. So we did insertion sort, selection sort, heap sort. OK. So we did heap sort in lab, kind of. OK. Here's what we did in lab, and I mentioned this a little bit earlier. In the main.cpp file for the lab, what it did was it created a heap, right? Pointer's dead. Created a heap, OK? And then what it does is it actually copies the sorted version of the heap, which is what we created, into a, sorry, it takes the heap and removes the minimum values, because it is a heap. If you remove the minimum each time and then place that into a new array, if you do it in order, it'll actually go in order, right? And then it also does this where it actually takes the copies back into the original list that we were passed in this function itself. But so not in place in this case, OK? You've got the heap, which you create. And the heap allows you to remove elements, OK? It allows you to remove elements by the minimum efficiently, right? And then as you do that, you get it in the order of you get it in order, because that's the whole point. Okay? You can also just remove max as well, of course. Okay?
Why do you have to put it back into the original list?
In this case, why do you have to put it back in the original list? This was the way the program was written, in the sense that it was going to, I believe it was going to return the original list to whatever function called. I don't know if this was a calling one. I forget. Yeah, I forget exactly why it did that, but it wasn't. Either way, it wasn't efficient. This is probably the part that's this part's kind of an extra step you don't need to do. But this part, if you're not going to do it in place, you're going to build the heap this way. And you're going to put it into one extra array, which is going to double the amount of space you need. Yeah. OK? All right. Questions on that one? So that's what we did. But here's what we can actually do to make it to go in place. First, you heapify, which we already did. Once you've got a heap, OK, then you can actually do this. Iterate over the array, OK, and perform remove min. OK, well, actually, I guess iterating over the array is probably not the right word for it. Perform remove min, but instead of removing and like returning that minimum element, just swap it with the last element and decrease your heap size. I'll show you what that means in a minute. Okay? What you're doing is you're removing the min, but you're saying, hey, I've actually got this space where I just removed it from. Put that minimum at the end. Make the heap size one less so we don't consider that one again. If we didn't, then we'd be in trouble. Then you'd actually remove it and then bubble it all the way back up to the top again. Or rather, bubble it, I guess, bubble down, and it would eventually end up at the top. So you want to, the ones that are sorted, make sure they're in the same array, but not in the heap, which hopefully makes sense. You've changed your heap a little bit such that the array is being reused, but the heap is actually smaller. I'll show you what that means. Okay? When the iteration is complete, you're going to have the array sorted from lowest to highest priority. Okay? In other words, it's going to be backwards. But that may be the way you want it. If you happen to want an ascending sort, in other words, going from the minimum value to the maximum value, you're going to want to do a max heap and then do this procedure, and then do the sort from a max heap, and that will put it in minimum to maximum. Otherwise, it's going to be the exact opposite. Okay? Questions before I show you what it actually looks like? You already saw what it looks like in the thing. Yes, Rose.
When you heapify an array, does that mean you're putting it in order, but then the children aren't?
Yeah, good question. When you heapify an array, are you putting it in order? No, we are putting it an order, but it is a heap order. So in other words, all it has to be is a heap. In other words, parent, children are lower priority, children are lower priority. It does not have to be in any, in fact, most of the time will not be in an order where you can pick out, go through the whole thing and pick out things. You have to do a down heap each time. Like you have to do an actual remove and down heap it. So good question. But that's the whole point of building a heap. You get it into a heap form, and once it's in heap form, then it makes it easy to pick out the minimum values. That's kind of the whole point. Okay. So here's what it would do. So first of all, let's start with our unheaped. I'm gonna leave this in the sense that we're gonna start with 0. You can. I don't really care if you start from 0 or 1 with your arrays. For the homework, we'll have to standardize it. We'll probably standardize it on 1 instead of 0. But either way, that doesn't change the algorithm particularly. In this case, so we start with an unheaped value, and then we heapify it. Now that was like 2 lectures ago, right? We heapify it, or I guess 1 lecture ago, and then you practice this in the lab. So once we do that, we turn this unordered array, right, and in tree form it looks like this, into a heap, which in tree form looks like this. Notice it's not necessarily in any like picking out the total like count in sorted order. It's not sorted, and it's certainly not sorted here yet. Okay? But it is relatively easy to do that sort. Okay, it's relatively easy to do that sort. Let me show you. So you've got it in a heap form. Now, all you do is you iterate and you call remove min, and you swap with the last element. So we've got to know where the last element is first of all, okay? And that's at heap size, right? And so what we're going to do is we're going to swap 43 with the minimum, which is what we're trying to put in order. Okay, we swap them with the minimum. Okay, and then you have to, and then you know that heap size is 20 is now here. This too is like we get the space for free. We've kind of already gotten that for free because we just swapped it in, and now our heap is 1 less. Like our heap size is 1 less, but the first sorted value is right there. Does that make sense? That's kind of the part that is how we enable this to be in place. Okay, we've changed the heap size, but all we've done is move the root down here. But we're not done yet. We can't just do that swap. It'd be nice if we could. Once you do the swap, well, now we've got a heap that's actually not a heap anymore. We've messed up the heap property. This one does not count as part of our heap, right? So what we do is we bubble this one down, or down heap it. Boom, 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 and it down heaps like that. Okay, it's just a straight up down heap. But you don't take the 2, and it's not going to matter in this one, but in some cases you might get to a point where those roots are going to, or those leaves are going to, could matter if they were still in the heap. Yes?
Is it possible to manipulate this algorithm so that it does sort in order? Like you move, like you track the index where you're swapping instead of size?
You keep the index of where you're swapping. So what would it, I'm not sure I quite get what you mean. Give me an example of.
Like you stick, when you sort element 2, number 2, you stick it into element 1, and then you start the heap from element 2.
Here, and then you start the heap from element. Well, the problem is, remember, the heap has an ordering that's based on those mathematical formulas, right? So all of a sudden you'd say, well, if it was here, 43's parent, remember, well, it doesn't have a parent. 43's children, remember, are these 2 values. If somehow you had 2 here, it would still be that. Look, as I said, sorting is still kind of an open problem, right? So if you want to think about some ways to keep that in order, I would be willing to bet you might reinvent the wheel in some sense, but there is nothing wrong with that. Like, I mean, thinking these things through, lots of people have done that, and lots of people have like gained insight into it. So there's a lot to be gained from trying to figure that sort of thing out. So yeah, good idea. I don't think that would work in this case, but there might be. I'm just not sure. Good idea though. All right, so now that we've got 43 bubbled down properly, right, we go to the next. This is now our 5 bubble. 5 ends up at the top, and that happens to be our min, because that's the whole point of doing that, right? And then it will. Did I mess this up? Do I want to bubble up? No, I don't. I think we're OK. 5 ends up as the min, and then that will end up over. We swap it with the root. OK, yeah, that's the point. We swap it with the root, and then we bubble down the root. OK. Question? Yeah, question.
I don't understand what's the purpose. I thought when you have a heap, it's already sorted as the highest priority that the root
It is.
one.
Right. You're absolutely right. For a heap, the highest priority is always at the root. Okay? And once it's a heap, when you do that bubbling down, the next highest priority will end up at the root. So that is true. But that's the only one that's in strict order. Okay? And that's what's nice about the heap is that it doesn't actually matter if you just want the minimum value. You're going to get the minimum, and then you're going to be able to do that bubbling down and get the next minimum, and bubble down and get the next minimum. You see what I mean? The minimum always ends up at the root. Does that make sense? Let me go back one step here. Let's go back right to the beginning here. So we're starting out. We know that this is the minimum, correct? Okay, where's the next minimum? It happens to be here, but the next minimum after that happens to be here. Is this a correct heap? Let's look. 2's children are lower priority. So it is heap order this one. 5's children are lower priority. 10's children are lower priority. 8's children are lower priority, and 12's child is lower priority. So it is a heap, and it does meet the heap property.
Yeah, so if you
Right?
were to remove all elements, they would already come in order.
No, they wouldn't. How would you do it?
Because when you remove the root, you have to put somewhere there, and for it to remain as a heap, you'd have to change the property.
Well, that's what we're doing. But that is what we're doing, right? You just have to do the process of bubbling it down. So you're absolutely right, but you have to do the process of actually bubbling it down. So if we, you can't look at this and go through in any order and pick out in a linear order, you can't pick out what the next smallest item is, right? I mean, that's actually a very good question. For this heap, what's the second most, the second highest priority? One of the children, right? So you can check one of the children is definitely the second. What about the third most highest priority? One of the children of what? Well, maybe. I mean, one of the children happens to be the child of the 5, right? And then this one happens to be the child of the 8. But it could have been over here somewhere, right? It could have been this one, could have been the next one. So you can't go, there's no strict ordering to go through without doing this bubbling down to do it. Yeah. Make sure you convince yourself of that. That's kind of the whole point of heaps in general. Yeah?
And the reason why we're swapping the end is to maintain a small space capacity.
Right. We're trying to do this in place. And well, part of it is that way. But remember, when we do remove, what was the algorithm for remove? It was return, remove min. Return this, so get rid of the 2, and what do we put in its place? The last element. Right? So that's the one we're going to put in there. We're going to get rid of this element anyway. Right? And so by getting rid of this one anyway, we might as well swap it and have that place now used with an actual ordering that we care about. See how it works that way? Kind of cool that way. Okay, that it works out. Okay, let's look at let's do it again here. So we're going to swap that down. 22. Okay, so 5 is now the min. And we're going to swap it with the last element. And the last element now is 22, because 2 doesn't count anymore. It's just there for storage purposes. Okay? We're going to swap it with 22, and then we're going to down heap 22. And when we do that, 22 actually needs to down heap twice, and it will end up in the position of 9, and 8 will end up as the root, which is the minimum that's left in the heap, which is good. Okay? Same idea. We're going to do 40. We're going to replace 8 with the last element in the heap, which happens to be 43 right now, and then bubble 43 down. Okay, and then 43 has to go, it turns out it has to go left and then right. Okay, and by the way, notice it does not switch with this one. This doesn't exist in the heap anymore. Max or heap size is here. That's the last possible one that it could replace, because you've decreased the heap size. So far, so good? Okay. All right. And then now we do 9. And, sorry. I forgot to do the swap. There we go. 9 is now the root, which is the minimum value. Swap it with the last one, which happens to be 14 now, because the green ones don't count anymore. I tried to color code this the best I could. All right? And then you swap that, and then what happens? 14 has to bubble to the right and then to the left. But that means that 10 is now the minimum, et cetera, et cetera. OK? See how that one works now? Go watch the animations, or actually try to do it on paper. It's a good effort, or it's a good exercise to do this on paper too. You can see how all the swaps are happening and how it works. OK? That's the heap sort. So what's the complexity of heap sort? Well, remember, we can build a heap in order n time. Okay? This removing and bubbling down business for all the elements actually happens in log n time. Okay? And so the worst performance is actually n log n, which, as I said before, is the kind of the best performance in general that we can get for these kind of sorts. Heap sort's a pretty good sort. It's fast. We can do it in place. Best performance is also O log n, n log n rather, which means that it's not going to be super fast for things that are like already sorted. It's not going to actually make a difference. You're still going to have this n log n behavior. Average performance n log n, right? So this is like you want an n log n sort, use a heap sort. Works well, works pretty good, and we can do it in place. Okay. Tell you what, let's look at that video again, the fun one, and then I'll back it up a little to the place where it starts heap, which is, let's see, nope. Yes, maybe hang on. Yep. Merge is there. OK, let's see what this one. Oh, there we go. I think, there we go. This is heap sort. I don't know how informative this is now, but remember, it's building from the back, always removing something from the root. There we go. You want to see a couple more? This is what's called a radix sort. We'll get to that one. This one's a completely different type of sort, like absolutely 180 degrees different than the sorts that we've seen before. It's pretty fast though. If you have things in order. It's another kind of radix sort. I should give a test where it's like a history, what is it, art history test where I just make you listen and you have to tell me what sort it is. I bet you could do that. You could totally do that. You can memorize, you know. This one's the one that GCC uses in its sort function. I'm not sure exactly what the method is. It's probably a variation of, actually it didn't look like a quicksort, so maybe it did, I don't know. Kind of slow at the end here, yeah. Okay, yeah. All right, let's see, what else do we have here? Got any more? This is a GCC stable sort. You have a specific one that says, I guarantee you that it will be stable, right? I bet this one's the order n log n. Why? Because you can see it breaking it into halves, right? And then the green one. There you go. All right, one more. What else do we have? Oh, Shellsort. This is the one we're going to do next. OK? You'll see it and then figure it out. Okay. Notice something. Can you see the little range of bars going through there? It's going to become important in a second. Almost. There we go. All right, let's talk about Shellsort. OK? What's that? No, not bubble sort. Bubble sort's actually in there, I believe. But OK. All right. So the next kind, this is another sort that's a little bit different. This is actually called Shellsort. Before I knew what this actually was, I'd heard about it, and I didn't actually look into this like years ago. I thought it had to do with like you know how you like play the shell game where you're like, I thought it had something to do with like that sort of thing. No, the guy who invented it was named Shell. Like literally, like that's the name of it, right? Donald Shell is his name. This is very similar to an insertion sort except that it happens to be much more efficient. Okay? The interesting thing is that it's almost impossible, well, so far it's been impossible to analyze the average case for the generic shell sort. It is still a completely open problem. So if you guys want to get your math PhDs or your computer science, theoretical computer science PhD or something, you could a lot of people have worked on this. Like, this is a big problem. A lot of people have thought about it, but you never know. It's still an open problem. You can figure out how to provably show what the asymptotic complexity of shell sort is. Well, probably get a PhD. So here's what it is. Here's the general idea. Okay, in insertion sort. Okay, remember how we always kind of going back to the beginning or the last element at the beginning and kind of sorting and then sorting and sorting, and it's not so efficient. What this one says is rearrange the elements such that every eighth, that's hard to pronounce. That is hard to pronounce. If you go to the h-most element and then keep going on, produces a sorted list for that number that we are, what we call a hop, that we've actually gone to. Okay, so far, if our h was 5, that would mean elements 1, 6, 11, 16, etc. Add 5 each time, will be sorted after you do that particular sort. So you're breaking the problem down, and you're just saying, fine, we're going to sort parts of it in that order. Then you have a different gap, a smaller gap, right? And by the way, at that point, that's considered to be h-sorted. Okay? In other words, the hth element is sorted going along from all the h elements. Okay? I'll show you this in a second. Okay? And then what you do is you actually repeat that with a smaller gap. When you do the smaller gap, it retains the first sort that you did. So it doesn't change the order of the h sort. You do a smaller gap, what we'll call a k sort, such that every kth element is sorted. Okay, and it also retains the h sort. And then you keep repeating smaller and smaller gaps until you have a gap of 1. Yes?
So is there a standard number for h?
Great question. Okay, this is a great question. The question was, is there a standard number for h? Finding that gap, let me show you this, actually. Let me show you what this is. If we go back to here and we go to Shellsort on Wikipedia, right? We go to Shellsort. The gaps here, these are some different, like all of this is like somebody's decided, hey, these are a good formula for a good set of gaps, right? Here and then this one and this one, 2k minus 1, right? There's one that they use in the Wikipedia example here, which happens to be this way. Think of it backwards. What you would start with is a gap of 281, then 77, then 23, then 8, then 1. As long as it ends with 1, you can use any gap you want. Some happen to be better than others. Why? How do they become, or how do you know they're better than others? You do a lot of math, and you prove these things, right? So it's tough to come up with new ones of these, but there's a whole list of them. Yeah, and there's some that are better than others, right? Is there an interesting one, Rose? Oh, yeah, well, yeah, Cedric did 3 in a row. Well, probably because Cedric, that was like his dissertation, or that's what he does as a professor or whatever. He thinks about shell sorts, right? And you can do that sort of thing. And then, yeah, go ahead, Jason.
So how does it keep the h sorted?
How does it keep it? I tell you what, I'll show you what it is, and you'll see that it's not going to change the order of the other sort. You'll see. It's a smaller gap, so as it turns out, there's no real way for it to jump the gap and make one go back to a previous location. You'll see. You'll see how that works. Yes? Do you not want it to? You know, that's probably one of the things that makes it better, like having it say not go divisible like 16, 8, 4, 2, or whatever. That may be right. In fact, it would be kind of fun to try different gaps and see what to actually run them with different gaps and see what the performance is. I mean, this one is, let's see, this one's kind of like that. This one is, and it's listed there, right? But in this case, it's order n squared, so not so good. Yeah, so in this case, not so good if you do it that way. Okay? And then some of these get better in all these different orders that we've never talked about before, like order n to the 3 halves and what have you, right? And there's other ones that are better. And then down here, they still have no idea. Or at least the people who wrote the Wikipedia article couldn't figure it out, couldn't find it, right? So people have, like this guy, like these people have come up with new types of finding the gap ones that are, haven't been proved yet what the thing is. Okay? Yeah, somebody came up with this one. They didn't have a formula for this one. They're like, hey, this is a good one. Yeah, I mean, I don't know. I mean, there's a paper about it. I mean, again, nice thing about Wikipedia, right? If you go to 13 here, right, we could go find this. Probably on the, it's probably going to allow us. There it is. Okay, best increments for the average case of Shellsort. Da-da-da-da-da-da, right? And there's lots of math, and you can go read this, and it's got fun graphs and whatever. Okay, right? And it's kind of long, right? Nice and long. But there's lots of different, you can dig in and really see this stuff if you want to. Okay. All right, let's go back and see what Shellsort actually does. Okay. Okay. So here's the gap sequence we're going to use. It happens to be one of the ones on that list, just for only a few values here. What we're going to do is we're going to start with a gap sequence of 5, then 3, then 1, and we're going to do this each time. The 5 sort does the following. It says, go through the list and do the 1, 6, and 11, because that's 1 and then 6 and 11, just add 5 each time. And then do 2 and 7 and 12, also adding 5. And then do 3 and 8. Well, there is no 13 here, as it turns out, so you don't need to do the 13. That's going to be an easy one, right? And then 4 and 9, and then 5 and 10. And that goes through the whole list at that gap and sorts for those gaps. Okay, makes sense? Okay. All right. When we do that, these are the ones that are going to get sorted against each other. 62, 17, and 25 are individually going to be sorted. Pretend that's their own array. And those 3 get sorted in their order. So in other words, it's going to end up being 17, and then 25, and then 62. Okay? All right. How you do that sort is up to you, but it's generally going to be a small enough number of elements that you could use an insertion sort or some other kind of sort for that. But the point is, picking this is how we're going to is going to be the important part. And then the other one's going to be 83, 95, 28, and then 18, 86, etc. Okay? When we do that, and I'm going to skip steps, 4 through 15 or whatever, right? When we do the 5, the 5 sort, okay, we end up with the following. And I've tried to make it so you can kind of see what's going on here. This was the original order up here in the colors. Notice that the red ones are now ordered according to their position, right? So each 5th red one there is now 17, 25, and 62. And then the yellow ones are 28, and then 83, and then 95. Okay, those 3 got ordered. Okay, small numbers of n. You can do it very quickly and order them this way. Now you do the 3 sort. That's bumping it down to the next gap, right? That means we're going to do 1, 4, 7, and 10. There's actually going to be 4 values because it's a smaller gap. But we've already sorted some of them. So as it turns out, it's going to probably be OK. 1, 4, 7, and 10. So yeah, so 1, 4, 7, and 10 now have to get sorted. Now, sorry, who asked the question about whether it remains sorted? I forget who it was. But if the gap, that it's the previous gap, let's see if it makes sense. In this case, we've got, what's that? In this case, we've got, so 17, 47, 83, and 69. Those are not, they're always going to be in the proper order after we get done. And there should be no case where those swap one that was already completed. Like it shouldn't swap 2. It wouldn't be the case that it would swap 2 that were already in a different order and make them in a new order, because you're always sorting kind of right to left. Okay, so it actually turns out that it's fine that way. Okay, once we do that, once we sort it that way, we'll end up with a 3 sorted and a 5 sorted array, right? And this is what it is: 17, 7, 18, 47. You can kind of see I've left both of them up there. You can take the time, if you want to look at it later, to go with it there. And then finally, you've got a 1 sort, which is the last one you're always going to have to do, which will just say go through and do the whole thing. Now, most of it is done for you already. There's not going to be as much. It's just a normal insertion sort, which is generally slow, but you've done enough work that this will be relatively fast. Yeah. Did I mess up? Did I mess up on one? No. OK. Generally, when people are like, it means I messed up on one. but I'm glad I did. OK. Questions on how that one actually happens? It's a little trickier to actually code, for what it's worth, but it's an interesting one. If you pick the gap correctly, you will do better than an insertion sort. But we don't actually know what the average complexity is. In fact, we'll talk about it here. Worst performance. OK, this does have a worst case performance of n squared. Why? Well, because it could be in some order where, even though you're doing all the orderings individually, you have to redo all those orderings. And it's going to take n squared amount of time. Best performance, n log n, which is very good. We like that. Average performance, still an open question. OK, I think they figured out for a couple gap sizes and so forth. But in general, we do not know. Still an open question. OK, and it's an in-place sort. Notice we didn't need extra space for that. We'll get to ones where we do a little bit later. OK, questions on that? OK, now I'm about to show you. Let's see. I'm about to show you what I would consider the best video you will ever see in a computer science class. OK, hands down, this is the best video you will ever. And that's big words, right? Like, you could see some very good ones. If you take an architecture class from me, I'll show you a very cool one too. But this one it's phenomenal. And there are more of these too, so you can feel free to search for them. But take a look at this. OK, all right. These are Hungarian dancers. And they happen to know the algorithm for Shellsort. Let's see, what Hungarian dance sorts. See what they've got. OK, no, that's not what it was. Hang on, it wasn't dance. It was folk dance. Hang on. Is there a channel? Hold on. Where's the channel? Sorry, I'm stupid. Here? Yeah, all right. There we go. 6 videos. OK, let's see. Hold on. You guys know a lot more about this than me. There we go. All right, there we go. Quicksort, merge sort, shell sort, select sort, bubble sort. It's probably the easiest one they learned, the first one they learned. Notice it takes 5 minutes. And then insertion sort and with Romanian folk dance. Oh, OK. Oh, wait, it's all different types. Transylvanian, yeah, you know. There you go. All right, so anyway, hopefully, if you ever find a better video than that one that's shown to you in a computer science class, please let me know, because I think I'll find it amazing. OK, homework 4. It's going to come out tomorrow. I still have to clean it up. I am taking some of the suggestions that some of that feedback gave, and we're trying to broaden this to some extent. Here's what we're going to do. We're going to have you write 3 different programs that are sorting algorithms. OK? It is not that hard to write a sorting algorithm in general. One of those programs was going to be a selection sort. OK? And I will give you some code that sets that all up for you. OK? The other two, and you can use like the setup for that for your next for the other two if you want to. OK? For those people who are like, we don't write enough code, you will get some, but you'll have to write some other code as well. OK? One of the sorts is going to be selection sort. One of the other sorts has to be from the following list: shell sort, which we just did; merge sort, we haven't talked about yet; quicksort, which is a cool one; or insertion sort, which we've done before, but I'll allow it. All right, more or less. I mean, I'll allow it, but we've more or less done it before. We haven't done it in place. And we're going to talk about all of them that we haven't talked about yet, like merge sort and quicksort, before we get done with like next time. So if you want to do one of those, you can wait until the lecture if you don't want to start on it. You can't implement bubble sort or heap sort. I'm not letting you. OK? Heap sort we just did, because we just did in lab. And then bubble sort is just silly. So the third, you can also choose the third one from this list. That's fine with me. Or you can find any other sort you want. You want to come up with your own sort? That's fine with me. You want to go look up some crazy, weird sort that Tim sort or something, and you want to code it up? That's fine. I would ask that you please don't like copy and paste wholesale code. Like if you find C++ code, if you find an algorithm, that's fine. Don't copy like the C++ code. That's obviously not allowed. But you can look up algorithms and things. Obviously, you need the algorithm to do it. Wikipedia has lots of these algorithms on there, and there are other ones as well that lots of people have talked about it. Or you could watch Hungarian dancers do it if you want to figure out the algorithm that way. So this one's kind of a little bit more open-ended. Here's how we're going to test it. Okay, the way it's going to happen is you're going to basically run the program and we're going to input a number of numbers. It's probably going to be from standard in, C in. You're going to have a whole bunch of numbers, and then it will push them out in sorted order. Straightforward, right? We're going to check, obviously, that it's correct in the sorted order, and we're also going to time them. Now, the timing is not necessarily for your to say you did this wrong, but if some of these algorithms we're going to test on the worst case data, and if somehow you say, hey, I did a merge sort, and you end up with order n behavior, well, we know you did something, like you used something else that didn't make sense, right? If you actually do any of it in order n, you've broken the laws of like computer science, right? Like math, you've broken math. But so anyway, so we're going to time them, and we're going to just make sure that they sort properly. Okay. I hope some of you guys come up. If you want to do a little more work and come up with some cool sorting algorithms, it's kind of it's interesting to do. Go right ahead. If you want to like do the assignment and be done with it, I would pick some of the easier ones. One will probably be trickier than the others, just because there aren't that many easy ones. But I don't think it'll be drastically difficult in that sense. Okay. We're also debating like timing all of your best ones and seeing who gets the best one, and maybe I'll announce it or give a prize out for somebody whoever sorts our big list of numbers the fastest will get some sort of prize. So, questions on that? I'll have it out by tomorrow at some point. Questions? No? Okay. Then if there's nothing else, I will see you guys on Monday.